Hello, welcome to the today class. Today we will talk about BoW word, BoW model for local descriptors. So these are the today class objectives. One of them is that you need to understand the BoW word or the BoW visual word model, which which is considered as a pooling operator that we talked about the last time. Also, we will talk about some of the CNN-based approaches, especially for generating better CNN features by using these ranking laws. Also, before we move on to the today topic, I'd like to briefly review what we talked about last time. Last time we went over some of the main components of this convolutional neural net (CNNs). Also, some of the main concept was this local connectivity, also some of these pooling operator for generating invariant features. Also, I went over all of your questions. Also, I think that one of your fellow students has a very interesting question here. He think that he didn't find there many connections between the manual approach of deep learning, for example, even for SIFT, right? But also there are many people said that some of the old technology actually helpful for the new technology, right? But he doubted now because actually he saw there many the other cases, right? I mean, some of the recent deep learning actually doesn't have any relationship with the prior technique, right? I agree with some of his opinions. Also, he talked about he has some background on the data mining domain. Also, he said that he didn't find there much relationship between some of those concepts, right? And then he asked her, as a graduate student, how do you suggest us to learn the traditional algorithm, right? I think that this is a very interesting question. So I don't have the particular answer for that, but in my view, I think that the prior algorithm and manually created ones actually now some of them actually turn out to be inferior to the recent deep learning approaches. Actually, as you know, some of the deep learning approaches actually showing the better accuracy. Even actually there are recently there has been the local descriptors based on the deep learning showing the much better result to the SIFT actually. Probably later on I will talk about that approach. But nonetheless, actually, we can when I talked about the SIFT, actually, I can explain well, right? Basically, those prior techniques actually explainable. Also, as a result, they're actually understandable technique, right? In other words, they can give us the many insights to us as a human being, right? So one of the research direction of the deep learning is that to design explainable AI, right? So mainly because in the end, basically for us, the human being, we need to able to understand it. Also, we need to able to explain each underlying technique, also each outcome to the other human being, right? Basically, it doesn't mean the human is the most intellectual the being in even in the future, right? They could be the more intellectual idea than the human being, right? But anyway, for us human being, we need to able to understand this technique, right? So as a result, ideally we need to actually design this explainable AI. But some of the prior techniques, while they are showing the lower accuracy, lower performance, actually they can in a way they are actually explainable. So I think that this suggests that we can somehow combine them together. In a way, we can actually design kind of hybrid techniques between this learning technique. Also, there's some of the old technique. I think that there's some hope that we can improve we can design the very good. We can design the technique that with their high accuracy, also which also they're kind of explainable. So another aspect is that actually for deep learning deep learning technique is very data hungry, right? On the other hand, the prior manually created approaches they do not in some cases they do not even require any training data, right? So in other words, to address some of this data hungry problem of the recent deep learning, we actually using some of the older technique which is actually based on some of this model based or some of the prior this knowledge. So that's my view. So I hope that there could be we can actually combine this old and new technology together. The result which can generate better results, right? But it doesn't mean that actually it doesn't mean that everything should be explainable, right? Obviously, even though it's not totally understandable to us human being, also that technique can be shown the better result, right? But and in the end, you think about it, whether that is actually the sufficient technology to us. I mean, they are giving us the very good result, but at some case we cannot even understand, right? Then it is just magic, right? So we need to think about it. Ideally, we need to think about it, what we really want is the magic or not, right? But anyway, there could be many issues and many questions along the discussion. Thanks for bring up these questions. My explanation here is not an answer. It's just my humble response to this kind of grand question. Anyway, so let's get back to our today material here. I'd like to talk about the BoW visual world. The main idea is that there's basically before we having this image search, there has been a lot of advances under this text search, right? So when you have a lot of documents, right? We want to identify a particular document based on some of these text keywords, right? And then over there, actually, you can see that there are some of documents has a lot of these words, right? So it's very natural that to explain some of document as a set of this kind of the word, right? So basically, when you develop this image search, some of these initial techniques also they're based on this text-based search. Since actually they already know some of these text-based search, so they are showing the good result, right? So that's why actually we wanted to apply this concept here. What concept? There could be some of the words, and then based on that word, we can actually describe this main theme of the document, right? So here we wish that we can also define some of the words right here, and then once we define the word, in this case actually the visual word, and then we somehow have the visual word, we can actually represent this image as the BoW word, kind of histogram of the word. For example, we can actually, in this case, we can see the eye and mouth, something like that, right? And then we can describe that. As I said, if we can identify that kind of visual word, we can actually represent this image, saying that this image has one mouth, two eye, also some of these necklace, right? Based on that, we can do some other applications like image search, also even this classification. That's the main idea. Represent an image with a histogram of some of the visual words. The visual word is kind of the visual concept corresponding to the kind of the words in this text domain. So for example, suppose that actually we are a set of the images, and then we identify some other image patches, and then image patch we treat it as some sort of feature, right? And then in the category of face, we can see this kind of the image patch, right, as a feature, nose and eye. This is actually from the bike related image. You can see the saddle, the wheel, and the gear, and so on. Also, these are from this violin, right? And based on that, we can identify the common set of this visual word, right? That is also known as this. We can treat it as kind of this code word dictionary. These are actually dictionary that consists of many words, visual word. Here, we treated this kind of image patch as a visual word, and then based on this common set of the visual word dictionary, we can represent each image as a histogram of each common visual word. For example, given this image, you actually count how many image patch you can see that you can have it from this image, according to this image patch and this image patch. For human face, actually we can have this kind of patch a lot, right? Eye and some sort of skin related patch, but not that much on this kind of saddle patch, right? But on the other hand, for the bike related image, you can see that we don't have the many patches on those of these visual words, but actually we can have a lot of occurrence here. That's the main concept of the using this the common visual word and then using the this histogram of this approach. That is actually the nothing but backward visual word concept. Once we actually have this one, so after this the training time, so given this basically here I'm showing the input image, right? Starting from this training data whatever they are, we actually somehow extract the common visual word. Say let's say that this actually called the word dictionary, right? And then we basically starting from this the raw image, we represent those each image with this the backup visual word model, the histogram of the visual word. And then once we represent the image at that with this backup visual word model, then we can perform any kind of classification. Also, we can do this image search at runtime. This actual recognition time or the image search time. Given this query image, we also represent this query image as a backup visual word with respect to this visual word, and then we can do the actual classification or the image search technique. The backward visual word actually mainly commonly used for the image search. Also, this technique can be used for the other tasks like this classification. So, any questions so far? Is it clear? Yeah. Okay, thank you. So now I'd like to talk about some of this individual component of this approach. First of all, we need to identify the feature. We need to actually detect the feature, right? We need to represent, right? So basically here we assume that we represent image a set of the many local feature, right? And then basically to think about it, if you are using the local feature, then from one image you might have the 100 image, right? Given one image you can gather this 100 image feature, right? But some other image you might gather 1,000 image feature, right? Then it's a little bit difficult since there are actually varying number of image features, right? In one case it has actually 100 features, another image has 1,000 features, right? It's a little bit difficult to perform the matching with the different number of the features, right? So anyway, we even though actually we are using this kind of the local feature, we hope that we can actually somehow represent them in a canonical feature space, right? In that way, backward visual word actually they're doing that approach. So here, whatever image feature, whatever actual local feature you have, you're only using the fixed number of the visual word, right? Dictionary, right? It could have 1,000, 10,000 words, right? So whatever local feature you have, actually you only gotta suppose that you had actually the 1,000 visual word, then you actually have this 1,000 actually dimension. You represent this each image with 1,000 dimension of this visual word. That's the main concept. In a way, you can treat that this backward visual word model as an aggregation model, and then you turn this kind of image with local feature that has a varying number of the feature into the canonical space. That's why I said this aggregation model, or you can treat that as this pooling approach. Sometimes I may use the pooling or the aggregation. Anyway, we somehow combine these different number of features, local features into the canonical space, right? While maintaining their each individual the information stored in each individual this image patch. And then here we do not assume that in this context we do not assume that this global feature. Obviously, if you are just using the one global feature, we don't need this backward visual word, right? But in most of case, we actually combine this global feature with this local feature. So, and then for local feature, we can use this backward visual word model. And then one of simple, basically, when I talked about SIFT, we can detect some of a region, right? Key point, and then we can define the surrounding region. And then we normalize it. We actually orient we actually reorient the dominant direction into the canonical direction, and then we compute also the shift, right? But also we also using the CNN based local feature. Also we can use that kind of techniques. So somehow we extract the local feature, whether they are the shift or the somewhat recent this CNN based approach. And then we need to actually out of them many local feature, we need to identify this dictionary, right? This commonly appearing this visual word, right? So basically, we want to identify some of the these visual words, right? Maybe each visual word. We hope that each visual word may be corresponding to some of the meaningful visual patch. But anyway, we basically starting from a lot of the local patch or the local descriptors, and then we somehow map it into this feature space, and then here actually we define this visual word as some of the representative kind of the center kind of the cluster center of each the cluster in that space, right? So that's our definition here, but obviously there could be other definitions. But basically, in this case, in this context, we need to identify the clusters of some of the features, right? And then as a cluster, we can using the many clustering approach. One is the very common clustering approach is the k-means clustering. It's kind of unsupervised learning technique. So overall, it minimizes the within cluster sum of squares. So here, that's the definition of the mathematical definition of this one. Xj, you can treat each individual the feature, and then ui is kind of the center of each i's cluster, and we actually measuring L2 distance between them, and we wanted to minimize this within cluster sum of squares. Actually, here Sj actually the S is the number of basically our assignment, basically our clustering result. But here I'd like to show you this visual illustration. Suppose that starting from the initial this feature, right? And then we can randomly pick in this case actually we set that we wanted to identify 3 clusters. And then we randomly assign these 3 3 different clusters into some of random points. We said that this actually the red and green and blue, something like that. And based on that, we assign this other unassigned data to each cluster here. And then we actually measuring for each node, we measuring the distance from that node to each center of the cluster center. When we assign that data to this closest cluster. In this case, this goes to the red, and this goes to this green, and so on. Then we can get the initial assignment, right? But this actually, the initial assignment could be pretty bad, right? And then we repeat this process. For repeating this process, further this assigned data, we also compute the new center of the cluster. In this case, let's say that this could be the center. For this one, we treat that this is a new center, and for this one, this is a new center, right? Based on this new center, we actually reassign each individual data to this new center of each cluster. We keep doing that until we converge. There could be actually the k-means clustering has been studied a lot. There could be a lot of the variation, but that's the main idea. And then you can also apply this k-means clustering for computing the visual world. Of course, there could be many other directions. The actual definition of define this dictionary, but this is actually one of the very simple way of defining visual world. And then if we do that actually, if you apply this technique to some of the natural image, then actually these are some of the example of this computed dictionary, right? Some of the image patch seems like very simple one. In this case, we actually some color actually changing from top to bottom, right? Or here, just one edge. If you look at here, somehow this patch is rotated to there, right? Something like that. Just to contain only one edge, but some other one actually has more information. In this case, actually, we got these 2 edges. One, the color goes down and goes up, right? 2 edges. So which is actually having the more information to the more simple one. Then, as you can see that there are actually you can see there are other patches with more complexity actually. These are some of the example visual words extracted from some of the natural images. But if you actually extract this kind of the visual word from the kind of the very specific type of the images, in this case, I think that they extracted this code word from a set of this plane related image, and some of the visual word actually corresponding to the field, I guess. Yeah. And this is we apply this concept to the other specific type of the image set. I guess this is actually the motorcycle, something like that. Then some of the image patch corresponding to this kind of the handle and so on. So you can see that maybe actually if you're using the k-means, basically the computed cluster nothing but the image patch or descriptor that are commonly appearing from that set of images. But actually there could be a lot of issues, right? So first of all, when I run this k-means algorithm, we need to define we need to start with the number of the cluster, right? In other words, how many visual words do you want to use, right? It's a little unclear how many words do we have to use, right? We can use the 1,000, 10,000, and so on, right? It varies a lot, right? We can use if you use too many visual words, there could be the quantization artifact, right? Quantization artifact. So for example, we can use the blue color or the bluish color. What are their main difference between blue and bluish color? Something like that, right? It's some people say the blue color, some people bluish color. There seems to be different words, but basically it's nothing but quantization artifact. Also, if you're using too small color, it's not really the representative, right? So we need to hit the proper number of the visual words, but obviously it's really difficult. Also, we need to also running this k-means just takes a lot of computation. So that's another issue. There could be many other alternatives in terms of accelerating running the k-means by using the hierarchical approach. So some of you may look, if you are interested, you can look for a paper known as the vocabulary tree. We build this kind of the visual word in a hierarchical way. So we can build actually the kind of the tree of this word. Or to address this quantization artifact, basically here actually these are actually here D, E, basically they're actually some of different cluster, right? So if the sum of feature actually near this cluster boundary, right? But at that case, that feature very close to D and E. But if that feature is actually that feature assigned to D, then it's already difficult to see that image with that feature actually has the common characteristic with the cluster of E, right? That's actually the issue of the quantization. To address that issue, then they actually proposed this kind of soft quantization. In other words, here we just assign each feature into one of the cluster, right? In other words, we actually do the hard assignment, right? But here we can assign the soft assignment. In other words, basically we use some sort of weight. If there actually the feature located here, we can use this feature close to here. So we actually assign a little bit high weight to there. Also, we assign some other maybe lower weight to this cluster E. Since also that this feature also close to this B cluster, so we can actually do some sort of the weight to with the multiple cluster. That's the kind of the improvement over this kind of the basic this k-means clustering approach. Then once we actually define this k-means, once we define this kind of this visual word, the dictionary, then given this image, we extract the feature, and then we need to actually see that whether which cluster each feature local patch corresponding to here, right? And then to do that, we typically perform this nearest neighbor search, right? And then we actually measuring the distance between this patch and the center of each cluster. Then suppose that if this patch was closest to this center, then we assign that this feature has this feature assigned to this visual word. That's the word. That's how we work, and based on that, we can actually we can check how many words we can actually having from this image. Based on that, we can build this histogram of this level visual word here. So we can actually according to each individual visual word, we actually measure this how many times we can have that one. That's the frequency of the each visual word from this image. So in other words, we represent this image with this histogram of the bag of visual word. Any questions?
Features of many objects are actually unbalanced.
Yes, yes.
So if in a picture, if there are more than two objects, then one could be dominant.
Right, yeah. That's actually a very important issue. I mean, basically, that's also one of the actual. Basically, what he suggests is that here actually we are showing the one car. I mean, we are showing the one main car, right? But in some other image, we might have the many cars, right? And then some of the patch actually becomes more frequently appearing. So actually that part may be the dominant, right? So actually I will also get back to the issue later on. So that is actually the kind of characteristic we want to capture with this bag of visual word, right? So something actually appearing a lot, we want to actually capture that idea. But it also has some issues. So that's why we commonly adopting some of the normalization the process. I will get back to that issue later on. Okay, same process. So given at the training time, we actually given the image, we detect the code word, and then we represent each individual image with this histogram. At the runtime, we also starting from this image, we represent the image with the histogram of every visual word, and then we can also we can perform the many other tasks like the classification and also image search based on this feature. Also, I talked about one of your fellow students asked about in some case, I mean, some feature actually becomes very dominant. There could be a lot of issues, right? So that's why actually we can also talk about this TF-IDF. This also adopts from the text search. This also kind of waiting order this normalizing process. Its main idea is that there could be the many different words, right? But some of the words are actually more important than the other, right? For example, if you look at some of the English text, I can say that on apple, right? Or the apple, the orange, right? But actually the on or the, that word is very commonly appearing, right? On basically that actually gives us some information, but apple is actually much more important, right? Since actually that's the main idea. So even though some of the keywords are appearing a lot, in this case A and D, it doesn't give a lot of information compared to the other keywords like the orange or the apple, right? So we need to also consider that one. So that's actually the main idea can be adopted in the TF-IDF. TF actually this is nothing but term frequency, right? So if some image has basically if there are some of the objects appearing a lot, then obviously we say that image actually more relevant to that under that concept of that object, right? So term frequency. So here actually this term frequency actually you just measure the count. I mean how many times the certain feature appearing, right? Actually as you actually had that's the main concept. Here if I explain here, ND is total number of the word in the document, right? You got in the document, and then NID is the number of the occurrence of each individual word in the document, right? So main idea is that say there are two images, something like that, and one apple, two apple, right? And then if you wanted to identify if I want to identify, can you see that? You can see? 볼 수가 없어요. 여기 안 보여?
I feel it's okay. Yeah.
네, 보여. 확인해서 보이잖아요, 그죠? 보여요. 오케이. Okay, so suppose that actually here you have the two documents here, one image with one apple, another image of two apple, right? And then if you want to identify say in this case actually you search with the text like the apple, then obviously you can treat that the image with the two apples may be more relevant, right? That's the main concept of the term frequency, right? If there's some of the keywords more appearing a lot, then we give them more weight. But also we need to look at the other case, inverse document frequency (IDF). I think that since this concept from the text, I think that I will show you the. It may be better to explain the concept with the text. Suppose that there are two images, right? Here, basically this image has A and B, and this actually has A, right? And then I search the keyword with A and B, right? Which one I should report it here? So obviously the T is matching here, right? But in the case of IDF, main idea is that A is appearing every document in the DB, right? Then basically the keyword A doesn't give us any discriminant. Basically it doesn't discern the property of the different documents, right? So if there's some of the keyword appearing a lot, then obviously it doesn't matter. Basically, we can actually we should ignore this concept, right? This is the keyword, right? That's the main idea of the inverse document frequency. So then, basically, this IDF corresponding to here. Then if you look at here, N is the capital N is the number of the total document in the DB, and NI, this one is the number of the occurrence of the particular term in the whole DB. Then if I visualize it here. So if there some of the keyword actually very rarely appearing, right? In the DB, then this n divided by ni should be very big, right? And then everything actually governed by the lower function. Lower function looks like this, right? If the sum of the keyword is very rarely appearing, then this term becomes to the here. It goes to there, right? And then you actually get a more higher weight. We need to consider that rarely appearing the weight. But if there's some of the keyword appearing a lot, actually at extreme case, ni becomes n, then it goes to actually even the 0, right? It even goes to 0, right? We just remove it. That's the main concept of the IDF, TF IDF. So basically, it means that even though there are actually many visual words, the question is whether we have to treat it equally or not, right? And then this TF-IDF actually has a certain perspective. We need to consider this term frequency or this IDF term. So actually, this concept from the text search, right? And then also when I suppose in this case I extracted a certain feature, right? And then I need to measure the distance, right? I need to measure the distance between this feature and center of each cluster, right? It means that I need to measure the distance, and then I assign each individual path to the most closest this cluster, right? To do that, I need to have a definition of the distance, right? In other words, the distance could be actually measuring the similarity. But what kind of distance we have to use, right? The similarity is nothing but distance function. So one can use this L1 distance, this Manhattan distance. Basically, here this one is actually the visualization of the Manhattan distance from this measure from the center, and actually this showing the equal distance point within the L1, and L2 is Euclidean distance, right? You know that actually these are actually equal distance from the center. Actually, some people, depending on your task, you can use L1 and L2 distance, right? Also, you can also using the dot product between two vectors. Dot product actually measuring the angle between two vectors, right? So you can use the different actually you can use this different distance function. But some of the more advanced distance function is the known of this distance. Which may I just like this. I will first showing this one. I hope that you can see this one. If it is unclear, I recommend you to open up the lecture note and look at the lecture note here. Suppose that that's the actual center, and then somehow the data actually distribute along in this way, this kind of elliptical shape, right? And then if you're just using the Euclidean distance, like this L2 distance, given this suppose this center, we actually get A and B, right? And then which is the more close to the center from the A and B, and which one we should treat as more similar to the here, right? If you are using just Euclidean distance, then obviously this is more close to there, right? But we know that if we know the data distribution, right? We know if we know that, then B is out of that distributions. We should treat that this actually very more far away than A, right? So basically, that data distribution along that in this elongated shape, we might actually if we know that actually we can treat the A might be more close to there, right? That's the main idea that Mahalanobis with the distance we want to measure. So basically, how can you represent this kind of distributions? So actually, we using this covariance matrix here, the sigma. Sigma is nothing but the mean subtracted covariance matrix of the data point. Basically, the sigma is covariance matrix. So if we actually have this kind of the covariance matrix, just give us the variance along the different dimension, right? So that actually we can know that actually what are the distribution of data here, something like that. Then, if we actually using the inverse of this covariance matrix, it means that if suppose actually if we do that, in this case, this data actually more far away from here, but we know that actually standard deviation is actually more bigger along that direction, right? Then we cancel it. So that's why we wanted to take the inverse of the covariance matrix. If we cancel this standard deviation, we treat that this A is close to the there, and then in this case, our variance is very small. But along that line, actually, B should be treated located more far away from the center. That's why we take the inverse of the covariance matrix. That's the main idea of the Mahalanobis distance. But here I'd like to talk about the other direction. Ideally, this approach is that once we actually have the feature, right, and then between that feature we want to measure the distance, right? Along that line, we talked about the L1, L2, also even more this complicated distance, right? But another approach is that we can think about it. We can design. We can actually obviously using Euclidean distance much easier, right? Compared to using this complicated one, right? So some of the recent deep learning they just prefer to use the L2 distance since it's one of simple one, right? And then somehow we wanted to design our CNN network to provide provide a patch that give us actually the smaller distance for the actually same patch for the patch that coming from the same part of the object, right? That's the idea. In other words, we actually aim to learn feature representation mapping the sample patch with the simple L2 distance, right? So actually this could be the actual feature learning or this metric learning, whatever you can call it. Here actually we can use another different architecture known as the CME CNN. So why CME? Actually there are two different actually data pathway. Given these two paths, we go through the CNN. Usually this CNN may actually has they actually share the weight. I think that this notation indicates that this CNN use the same weight, right? And then we compute the dx1, dx2, this feature, right? And then based on that, we measuring we actually measuring the distance between them. So let me give you this concrete idea here along that line. So now suppose that given this patch A, I can define some of the positive example. It means that the positive means that it actually from the same object. It should be the same patch, right? It should be the same object like representing same one. And then C is negative image. We know that actually this patch from the maybe the different object, something like that. Then our goal is that we actually compute the feature here. We run the CNN feature and then we somehow compute the feature f of A, f of B. But here, we ideally, if you're using the L2 distance, our goal is that the distance between A and B should be smaller than the distance to the A and C. Why? A and C is different one, right? They got to be the different, dissimilar. So they should have the very far away distance if you're using this feature, right? And then also in other words, actually this feature they are from the same positive set, so they should have the smaller distance, right? Here like this, right? So along that line, we wanted to construct a feature. That's their main goal here. So basically, allow us, based on this approach, we can allow us to learn the ranking between the sample, right? This is actually giving the ranking between these two different set of the patches, right? Also, this is actually known as the ranking loss or the triplet loss. Actually, here we are using a set of 3 image set, right? Given the anchor point, it's the positive, also the negative. It's a triplet set, the triplet loss or the ranking loss. So then how can you construct this kind of image set, right? Also, over there, we can also using the debugger visual work, this classical approach. So we actually here suppose that you can grab a lot of images from the web, right? We actually Googling, we actually crawl a lot of images, and then we actually we extract the sift order, we we perform the debugger visual work, and then we do the matching over there, right? We do the image search, and then based on that, we can also then we can cluster, we can identify a set of the image that are from the same landmark, something like that, right? And then based on that image, we do the matching, and then we can run the structure from motion, SFM technique. I didn't talk about SFM here, but that's one of classical computer vision technique. But what it means is that given this matching pair of the image, we can construct this kind of 3D geometry, right? So once you do the matching, then by running the SFM structure from motion, you can compute this kind of the 3D model, right? We can construct the 3D model from this classical debugger visual world approach based on image retrieval, right? When given a set of image, we identify the similar image, we keep increasing, and then we build this kind of 3D model, right? Based on that, from here we can identify the positive and negative set, and then based on that we can refine CNN feature by mimicking this debugger visual world, actually the matching or the retrieval actually. Let me show let me explain here. So given the query, once we actually handle this information, right? Once we know that these images from the same model, right? We can treat that they are in the same set of the data, right? And then given that the query image from that set of the image, we identify the top one. In other words, most closest image based on the existing CNN feature, right? Or we can using the top one, another top one with just using the debugger visual world feature, right? Basically, they are from the same set of the data, right? There could be some variation of the image, but we already know that they are from the same set. So, given the query, we treat that they are positive, right? We can even choose the random data from the image set. We know that we know that they are from actually the same landmark, something like that. In other words, basically, this actually we know that they are more close, very close to each other, right? This is more close to each other. But if you are using the random image from top K based on debugger visual world, you can see that they looks like different, right? So it's very difficult to do even the deep learning. But we hope that when you're measuring the edge distance between feature of this query and feature of this one, we hope that we can actually compute the feature that give us the very small distance, even though they looks very different, right? That's the main idea of this positive. And the negative one is we just actually identify some random image, right? Then it could be the random, right? But more important is that we want to identify the hard negative. It looks like this query image, but it should be the different image set. For example, if we do this kind of clustering, there could be the other landmark, right? Some of the landmark from the Eiffel Tower, some other one, right? We know that they are different, right? We know those patches look very different. They are from different cities, different landmark, right? But we actually identify the visually very similar images to the query from the different 3D model, different landmark. They look very similar to each other, but we know that they are different, right? Then we can treat that they are actually very difficult, basically hard negative images, right? Then by using this one, we can actually create our feature to have we actually learn the feature that differentiate the ranking between them. So some of you may wonder why we need to define the hard feature, right? We can just using the negative feature, right? You can do that, but suppose actually suppose this is kind of the classification boundary between the model A and model B, something like that. Whatever A could be the A and B could be the some arbitrary number, right? But you can find the sum of feature here and there. You can identify the sum of image in here and there, right? Then if they're looking very far away, I mean if those two images looks like a very dissimilar, then it's very easy to do even deep learning, right? By identifying a very hard negative, we actually suppose that this image should be the A, this image should be the B, but they look very similar to each other, right? But we know that they are different, so it looks very difficult. So in other words, by using this kind of hard negative mining, we can define very carefully this boundary shape between two different classes. That's why it's very important to identify the actually hard negative, something like that. That's why this technique adopted this approach. Does it make sense to you?
Yeah.
Okay, thank you. Now it's time to talk about the PA2, actually PA1. The PA1 actually there's optional, right? So actually this is PA, I would say this PA2, but this is actually our first program assignment. So I think the TA will upload this spec of this homework. It's nothing but you just need to understand and implement the basic image retrieval system. And then you can use some of the very simple the benchmark, and then then you actually run your image search, and then you measure the accuracy of your approach. So here I think that you just need to you can just using this CNN based feature. So given the image, you extract the feature and you run some of the actual basic image search system. So the details will be available at the spec of the PA, this program assignment, which will be available at the course homepage, also KLMS the homepage. So far I talked about BoW visual world, and I talked about the distance function. Also, I talked about the CNN-based approach. Here, I talked about it. I actually talked about the triplet loss and that kind of approach. And now, also in their prior technique, they also had the block. Basically, at the BoW visual world, we count the number of shifts, some of the feature assigned to each cluster, right? Basically, we just measured how many occurrences we have. But it doesn't matter. We didn't really care whether that feature close to center or close to boundary, right? But depending on your application, that measuring distance could be very important, right? So blood actually compute the distance difference between a feature and and each close center. So you're actually measuring the distance between feature and center. This also this first order approximation. Before this one, we just checked whether the feature is in the cluster or not. But here it measures the distance actually. And this actually plot here. Here actually, since we're measuring the distance, we can visualize the vector shape, right? Now here I don't want to talk about all the low level details here, but this actually blood shape, blood feature, coming from this image, and then this very similar image to there, and then you can see that the blood feature looks very similar to each other, right? This one, this image, this blood feature coming from there, this feature coming from that image. You can see that they are also similar to each other. I know it's very difficult to see that, but for the different images, they are, you can see that there are varying these feature shapes. Typically, in this case, actually, the blood descriptor used the 16 cluster. And then basically there has been shown that blood actually showing the better results over the BoW visual world. Basically blood encoding the more information than the BoW visual world. And also there's one of your fellow students mentioned that in some of the cases actually here I will talk about here. If you look at also blood, basically here actually blood has in this case blood has about more than 8,000 dimension, right? But the first dimension we measure the variance, right? We can see that some of the dimension has a very high variance, but some of the dimension has a very low one, right? So here actually since actually we can have this varying number of the variance, right? Then you can see that you can see that the difference, this dimension may play more bigger role compared to the other dimension has a small variance, right? So if you just measure, so basically there's some difference here will have the more impact than the other difference here, right? Since it gives a very small the variance. So basically if we do the L2 normalization, in other words, if we actually normalize each individual dimension, the element with the variance, then actually if we do that kind of normalization, it has been shown that it gives us the better one. Also, here there are many windows, right? In this case, actually there are some of feature, some of dimension actually corresponding to some of feature. I don't know which one. Some of the dimension actually corresponding to this kind of shape a lot. And then there has been a lot of occurrence over there, right? And then this is actually known as this kind of burstness of the some of feature, right? And then if we have this kind of cases, actually some of the dimension corresponding to here dominating a lot of things, right? And then we need to have also in that case, there has been known that de-emphasizing this kind of effect showing the better accuracy. So to do that, actually we are performing this square root. So we actually de-emphasizing the kind of very high occurrence of this kind of dimension lower. And then I didn't really talk about here, but they do all kinds of other normalization. So here I talked about their different cluster, right? 16 cluster. Also we do within cluster actually this normalization. If they do that, they actually have this kind of the very well balanced variance over the different dimension. And then it has been shown that this actually the normalization give you the better result. The main reason why I talk about here is that each individual the technique also important, but the more important is that you need to think about it actually this kind of normalization, right? Whatever feature you have. So at the case of deep learning, we talked about different normalization, right? We talked about the contrast normalization, other one. But the main idea is that we somehow wanted to have this kind of well balanced actually the features. So now here actually this actually kind of the classical concept of blood, right? But when I also look for another paper, the blood, I actually searched for the blood-based active learning. I found this paper. This is actually net blood. This is CNN architecture that generalizing that they're making turning this blood into the learnable techniques. So in this paper, actually, they wanted to identify the location of the query imaging, right? So basically, if we take this picture, we want to know. If we have this picture, we want to know that what are the location of the location where the picture actually taken, and then also we can also apply this technique to even this autonomous vehicle, right? So here for driving the car, for autonomous driving, we definitely need to know the location of the car, right? But what if GPS is gone, right? GPS is broken. And nonetheless, even at that case, we need to identify the actual location. Then we can utilize this kind of one. But for achieving their application, they use the blood-based approach. They talked about that. They explained the classical blood approach. Given this image, we extract the sum of feature, right? Fifth feature in this case, and then they do this bagel visual word or the blood, some of the aggregation process, right? And then based on that, they design their deep learning. Here, starting from the image, they actually they use this CNN one, but overall at the end of CNN, we just using the CNN feature, right? But basically, we just using the feature as we use the feature in the classical approach, and then they wanted to use some sort of blood approach actually. How can you do that? At the blood, basically the blood, we need to measure the distance between the feature and the center of the feature, right? So to do that, actually, they actually measuring measuring that distance. But the problem is that at the case of blood, we need to assign a feature into one of the cluster, right? That's the hard assignment. But it turns out that that's not differentiable, so that we cannot use that kind of hard assignment into deep learning. So to design the differentiable technique, they also use the soft assignment. Away from the hard assignment, they use the soft assignment. along the software assignment, they look like this kind of actually this function actually this common softmax approach used a lot in some of the deep learning approach. So I'd like to point out that I didn't actually prepare this slide further answering to the question that I talked about at the beginning of this class. But actually, I wanted to talk about this approach is that we can design some of deep learning based approach based on the concept intuition that we got in the prior technique, right? Obviously, it's not really equivalent each other. But if we explain this if we explain this prior technique, it's much more easier to explain our concept, right? So that's the kind of I think that they wanted to design also the technique that we can explain well to the reader of the paper. I think that's one of the reasons why they talk about this approach. And then obviously we can adopt the prior technique directly here. For example, for the deep learning, we need to have this kind of differential approach. So that's why they changed the hard assignment to the soft assignment. Okay, so far I talked about the BoW visual world, also some of the deep learning techniques related to the BoW visual world, also the blood. But BoW visual world has a lot of information, but it didn't actually. There had some of limitation. As you can see clearly, when you look at the human face, we can also identify each individual component of the human face, right? But we know the geometric, the relationship between them, right? But at the BoW visual world, we don't have any geometric relationship. That's one of the issues of the BoW visual world. So then the last time, also think about how we can actually consider this kind of geometric configurations from this kind of different patches, right? Along that line, I will talk about some of the techniques for ameliorating this issue later on. Okay. Again, I wish that by now you can understand some of the main concept of the BoW visual world, which is actually you can consider this as a pooling or aggregation method. Also, I talked about some of the ranking laws for the CNN approach. So I talked about the classical blood or some of the variation of blood into the deep learning. Next time I'll talk about inverse index that can enable the very efficient image search out of a lot of the image set. That's it, and thank you for the listening. Bye. 네, 감사합니다. 좀 이해가 됐나요?
네. 좋았습니다.
네, 고생했어요. 이게 뭐 Q&A를 하는 게 아니라 이렇게 줄줄줄 나가갖고 이게